Hello, and welcome to this webinar on the GitLab Admin Fundamentals. This time I'm going to discuss GitLab runners or the runner fleet. I want to walk you through a few topics. So you want to go over the runner architecture, what are executors, scaling runners, long polling, and then a bit on dashboarding. So let's go into it. First, the GitLab runner architecture. So what is a GitLab runner actually? GitLab Runner is in fact a lightweight agent, a very small process component that runs on any system or device or whatever. It can even run on your laptop. Typically, it runs on a server or a Kubernetes cluster. But I've also seen setups where it runs on a Raspberry Pi or some other hardware device. Because the runner is a very lightweight agent, it can run on almost everything. Even on Windows, macOS, and Linux. So GitLab doesn't need to know where the runner is living. It doesn't need to be able to access the runner or the machine where it's running on, because the runner will always pull back into GitLab. Now, how is that designed? So yeah, you know about pipelines. Pipelines have a CI job or more than one CI jobs. These CI jobs typically have sort of a script that needs to be run on some kind of runner. Now, when a pipeline is executed, is triggered, then GitLab at that moment dynamically determines which jobs belong in that pipeline. That can be different per pipeline run depending on the settings and the situation, etc. And those jobs that are part of that pipeline are then added to a Sidekick queue. As we've seen before, Sidekick is a component in GitLab that is responsible for background tasks. So it's queuing this job. And then a runner will pull into GitLab to ask, okay, what's the next job to pick up? And it will receive the job details. Now, a CI job is run on a runner, and a runner will delegate the script task to the executor, where the actual script is then executed. A runner and a job both can have tags. A tag is like a sort of a small piece of text, a word or whatever, that can be added to a CI job configuration, but also to the runner configuration. So when the runner pulls into GitLab to ask for the next job, GitLab determines on a few criteria which job is given to the runner. First of all, it depends on where the runner is configured. If you have instance runners, but the job is run in a project that only allows for project runners, then the runner is not giving that job. So if it's a project runner, then you will give it. You can also have group runners, but depending on where the runner lives and how the project is configured, you might decide which job to goes to which runner. Also, runners may be defined as protected. That means that runner only takes jobs that run from a protected branch or a protected tag. If that runner is then configured as such, it will only take jobs from the queue that are triggered from a protected branch or protected tag. And then the last one is the tags. If a job and the runner have the same tag, then the job is also handed to the runner. If there is a job that can't find a runner that matches all these criteria, then that job will never be run, never be executed, because it will sit in a queue until a runner comes that has all the prerequisites. Now, how does it look more technically? We have GitLab here, which is the GitLab instance, and the GitLab runner here. So you can, this is a very technical image, but let's divide it into two sections. You have the registration section and the job requesting and handling section. With registration, what happens is the GitLab runner will call into GitLab with a registration token or some other kind of token, and it will receive an authentication token in which the GitLab runner can later then ask for jobs. This registration process happens whenever a GitLab runner is started. Then it is registering itself to GitLab and receive an authentication token so it can authenticate itself with the follow-up pull requests. Now, when a runner is doing a pull request, it's doing it like every 3 seconds. You can configure it, but let's say 3 seconds is the default. It will ask GitLab, hey, is there any job in the queue that I can pick up? If there is a job, then GitLab will respond with the job payload. If not, it will get a response code, like I think it's 204, but it gets a different response code. But let's say there is a job, it will receive the job payload, it will delegate that payload to the executor. Executor will then download, clone the Git repository. It will download any artifacts or caching objects that have been defined, and then executes the script inside of that executor. Then after that, based on the output of the script, it will return the job output and status. Output is the log files first to the GitLab runner and then back to GitLab. This is in short how such a query runs. Now, as I said, the GitLab runner depends on executors. And this is an important section because there's quite a few different executors that you can configure in a runner. Now, here is an overview of all the executors we have. We have the shell executor, the SSH executor, Kubernetes executor, Docker executors. We also have virtual machines that we can support, and even virtual machines in the cloud. Now, let's go over these. Sort of the basic ones are the shell and SSH executors. These typically run on a small device or simple server. You can use them, for example, on Raspberry Pis, etc., like very small, simple devices. That's where they are mostly used. The runner starts an executor process, which is simply a shell process, and run the script in it, or it will start an SSH session to run the script on a remote machine. Now, because these are so simple, it's on one VM, there's no isolation, there's no sandboxing. All builds, all jobs will share the same environment, the same server, same file system, etc. So there is a risk of data getting shared between jobs. If you are within the same project, then that's not a problem. But if this is like an instance level runner, then there might be that risk. But as I said, if you have a very specific situation with hardware or Raspberry Pis that you need to run this, then this is a very simple and easy solution. Also, it has little ramp time because both the runner is living and always on. So once a job comes in, it can simply spawn a shell process and run the script. And caching is very easy because caching is only downloaded every other time. So once the cache is already there, or for example, repository data is already there, it can simply fetch updates and it's easier to start. Now, mostly used are, at least on instance level, are container executors, Docker or Kubernetes executors. A Kubernetes executor typically runs inside of a Kubernetes cluster. So you have a separate pod with the runner and then pods for the executors. And the Docker executor is a runner process on a VM, which will call into the Docker engine to start Docker containers. They are highly scalable, but also well isolated. So a container is on its own quite isolated, as well as Kubernetes pods. They run in their own sort of sandboxing environment, as long as you don't elevate writes inside of Docker, of course, because if you do that, then you might end up having it less secure. But if you keep your Docker security measures in place, this is a fairly safe way to run builds. Now, it does require some ramp-up time because once a job comes in, the runner has to spawn a pod or start a container in order to run the script. and that takes a little bit more time. Now, even more time is with VM executors, with Parallels, VirtualBox, or Docker Machine. The degree of isolation is very high because it's not just virtualization on sort of containers, but on entire virtual machines. So you have very high isolation, but also the ramp-up time is higher because it has to spin up an entire new virtual machine rather than just a container, which takes a bit more time even. But it's a very good way if you really need proper isolation. Now, on that same level, you can also have cloud instance executors. It works but similar to virtual machine executors, other than with cloud instance executors, you have like a VM image, that you define on either Amazon, Azure, or Google. And that VM image you connect to a, how's it called again? To a auto-scaling technology. So auto-scaling group, for example, or the similar tools in Google and Amazon and Azure. That auto-scaling group, or whatever it's called, has to scale by default to 0. And then there is a runner manager that will scale it up or down depending on the traffic and the demand. So this is a way to spin up very specific virtual machines. For example, I know that in the automotive industry, there's quite specific demand for virtual machines that run a certain scanner or test tool or whatever. So you can have that specific image prepared, and then it will be automatically scaling up and down based on this configuration. So it's a scalable solution with very specific scenarios. Let's see about scaling runners. Auto-scaling happens the best on Docker machine or Kubernetes executors. But as I just mentioned, if you have very specific situations, these cloud instance infrastructure also scales very well. But that's still like a beta feature. It's not yet in production. Docker machine and Kubernetes are in production. Docker machine, again, high isolation, but a little bit more ramp-up time. And there is a runner manager that will manage the amount of VMs that are available at a certain time. It will scale that up and down automatically based on the demand. And a CI job that is picked up is then delegated to a VM to run inside of a Docker image. For Kubernetes, it's similar. You have a runner manager that runs in a pod inside of a cluster. It can create multiple runner pods to poll for jobs. And the CI jobs are then delegated to a pod, and each job runs in a separate pod with multiple containers. So there's a container in the pod for managing the traffic with GitLab, but there's also a container with the actual image defined in the job where the script runs, and there might be some service containers. Now, how do you configure this auto-scaling configuration? You have basically two main attributes, concurrency and limit. With concurrency, you limit the total number of jobs that can run on the same cluster or environment. So you have a runner configuration. When you install a new runner, you have a runner configuration, and within that runner configuration, you can define multiple runner workers. And each runner worker can theoretically have multiple different executors, but often it's the same executor. And these runner workers can then spin up jobs, executor jobs, or sub-processes where the job is running in. So, for example, if you have a shell executor, you can say, I have 3 runner workers, all 3 are shell executors, and each of these have a limit of 5. So each of these workers can spin up 5 sub-processes, shell processes to run a job in. But if the total concurrency is 10, then there can only be 10 jobs in parallel at the same time on that machine. So all 3 workers can totally maximum run 10 jobs at a time. Now, with autoscaling, for example, if you have a Kubernetes runner and executor, then the limit defines the number of runners that run in total in the cluster. So let's say you have a Kubernetes executor worker with a limit of 3, then you have 3 runners runner pods created in the cluster that all pick up jobs. And the concurrency is then the total number of jobs that can run on the cluster. Cool. Now let's imagine you have hundreds and hundreds of runners on your instance, either on group level or on instance level, and they are flooding your instance with requests. Yeah, that might slow down your instance. For example, you have 500 runners. As I said, each runner will poll by default every 3 seconds. So that will be 500. That's wrong. This would be 150 approximately requests per second. Now, you can imagine if you have such a high load, that might lead to high CPU load on the workhorse or on the Rails nodes, and that may lead even to longer queuing times for your CI job. So people start complaining, my pipeline is not running, or it takes a long time before jobs are getting started. Now, we want to reduce the load on our system by reducing the number of requests coming in. We can do that through long polling. So what does long polling do? There's a very broad view diagram in the documentation, but in short, I would say long polling is a configuration where the number of requests is reduced because each request that comes in for a poll request for new jobs is held back for example, 50 seconds. You can configure that, but let's say it's 50 seconds. What happens? A request comes in, the workhorse will stall the request, will keep the request open. In the background, it will subscribe the runner, so to say, to a public subscribe queue in Redis. That public subscribe queue is listening to a queue where jobs are posted. So when a new job comes in, it's posted to that queue. Then when the job is posted, the subscription will pick up that job and will send that back to with the request. That means that instead of every 3 seconds, a runner polls only every 50 seconds. And once a job is available, it will automatically fetch that job and bring it back to the runner. That reduces the poll time a lot. Now, how to configure that is in the documentation, but it's basically setting a specific flag in the GitLab RV file to enable this feature. Then, now, imagine you have 500 runners or even 1,000 runners. You want to manage that a little bit and to see where problems are. Within GitLab, we've built in some dashboards where you can view what's happening. We would also advise you to use Prometheus and Grafana to collect data from runners at real time and put them in the dashboard, but also put alerts on it so you can proactively react. But let's have a look at what GitLab provides. So first we have the runner dashboard. It's an overview of all runners, not only on instance level, but also on project and group level. And on this dashboard, admins can configure the runners, pause the runners, start and stop the runners, but also can look into what's happening, which jobs have been picked up, etc. You can also see a median job queue time, so you can see a little bit on, okay, how long is the job queue, how long are jobs waiting in the job queue. That's also an indication on performance of your CI pipelines. Another way to look at it is go through the job dashboard. The job dashboard gives you an overview of all jobs running within your instance. You can see on the job status if it's passed or failed. So if a team is complaining, you go to the project, filter by project, and then see the status of these jobs. You can see whether they are pending or failed or whatever. You can also go to the runners, see which runners are connected, etc. So this is a good way to troubleshoot if teams are complaining. Also, we are working on a new feature called the runner fleet dashboard. This is an ultimate feature which is currently in beta, and it gives a little bit more detail on what's happening with your runner fleet. So not only just simply an overview of all your runners and all your jobs, but really, okay, which jobs have run in an error lately, or which errors have occurred on several certain runners, or etc. You can also view a bit of historical data here if you install ClickHouse. ClickHouse is a data warehouse solution, open source. So you need to install that separately, but then GitLab will push data into ClickHouse to be able to get some historical data. And this can also help in leveling out the loads. If you see high peaks, then you know, okay, we need to add more resources to our clusters, or no, you can sort of level out a bit what the load will be. Cool. Now, with that, I would like to thank you. This is my view on GitLab runners. See you next time.